All right, let's dive into this quantum computing stuff. Seems like you've been digging into some pretty complex topics. Quantum information processing, huh? We're here to break it down.
Yeah, we'll try to unpack it all, help you
Mhm.
find those insights.
Okay, cool. So we're talking about a totally new way of computing, right? Not just like faster processors in our laptops, but something completely different.
Absolutely. Even though, classical computers use quantum mechanics a little bit.
Oh yeah, like what?
Semiconductors, for example,
Uh,
they don't really use those special quantum properties. Like imagine having a super fast car, but you're stuck driving in first gear.
I like that. Okay, so like even if my CPU uses transistors and
Yeah.
those rely on quantum mechanics, we're not really using quantum mechanics to compute, right?
Right. One of the sources you sent over had this quote by Charlie Bennett that really stuck with me. He said that a classical computer is basically just a really slow quantum computer.
Whoa.
What he meant was, we've been using quantum mechanics all along, but we're not really taking advantage of it.
That's a cool way to think about it. So how do we shift gears and use quantum mechanics for computation? That's where the qubit comes in, right?
Bingo. You can think of the qubit as the quantum version of a bit.
Okay, I remember bits from computer science class.
Yeah, so a bit can be a 0 or a 1, right?
Mm-hmm.
Well, a qubit can be those two, but it can also be in a superposition,
A superposition.
which means it can be 0 and 1 at the same time.
Hold on. How can it be both?
Yeah, it's kind of mind-bending. It's one of those really counterintuitive parts of quantum mechanics. Think of it like a coin spinning in the air.
Hmm.
Before it lands, it's not heads or tails yet.
It's both, kind of.
Exactly. It's kind of a blur of both possibilities.
Hmm.
And that's sort of like a qubit in superposition.
Okay, I see why people say this stuff is hard to wrap your head around. So qubits are in this fuzzy in-between state, but how do we actually describe that mathematically? I saw something about probability amplitudes in one of the sources.
Ah, great question. That's how we quantify this superposition idea. See, normal probabilities, those are always positive numbers. But probability amplitudes can be, get this, complex numbers.
Oh, back to high school math class.
Uh-huh, yeah. So you can picture them like little arrows pointing in different directions on a plane. And these arrows, they can interfere with each other. They can reinforce each other, or they can cancel each other out.
Okay, so that doesn't really happen with regular probabilities.
Right, that's something unique to the quantum world.
So these probability amplitudes, they're like the recipe for how likely it is that the qubit will collapse into a 0 or a 1 when it's measured, right?
Exactly. And to make it even more interesting, these probability amplitudes determine how we represent quantum states mathematically. Remember seeing those weird symbols in the sources, like the 0 with the bracket and the 1 with the bracket?
Oh yeah, the cuts?
Yes. Those cuts are just a shorthand way of representing vectors. And those vectors, they're how we describe the state of a qubit.
Okay, so we have the state of a qubit as a vector in this special quantum space. And the probability amplitudes are what define that vector, right?
You got it. And this vector thing, this representation, is really useful because it allows us to describe how quantum states change over time. We can describe that with linear transformations.
We're getting a little mathy here, but I'm still with you. So we have these qubits in their superpositions described by these vectors and these probability amplitudes. How does this translate into making quantum computers powerful?
That's when things get really interesting. You see, adding more qubits, it doesn't just increase the information you can store, like with classical bits. It actually makes the whole system exponentially more complex.
Ah, right. Like how a 100-qubit system would need 2 to the power of 100 classical values to represent it, which is like way more than all the atoms in the universe.
Exactly. That's the key right there, that exponential scaling. That's what allows quantum computers to do computations that would take classical computers forever, like literally longer than the universe has existed.
Wow, that's mind-blowing. But how do we actually control these qubits? Make them do useful things? What are the tools we have?
That's where quantum logic gates come in. Think of them like the logic gates in classical computing, like your AND gates or AIR gates.
Yeah, not gates. I vaguely remember those.
Right. So instead of manipulating bits, these quantum logic gates manipulate the state of a qubit.
Okay.
So instead of like AND or not,
Yeah.
we have quantum versions of those gates, and we can combine them into these complicated sequences to make quantum algorithms.
It's like programming, basically.
Pretty much. The simple example is the quantum NOT gate. What it does is it flips the state of a qubit. So if you apply it to 0, you get a 1. and vice versa.
Okay, so that's like the quantum version of flipping a switch, I guess.
Exactly.
Yeah.
But things get way more interesting when we start dealing with multiple qubits.
Right, because then the interactions get more complicated.
Yeah, and that's where the real power of quantum computing starts to show up. For example, take the CNOT gate. Yeah, it works on 2 qubits. So what it does is it flips the second qubit, but only if the first qubit is a 1.
So it's kind of like a conditional gate.
Exactly, it's conditional. And that's how we create entanglement between qubits.
Entanglement. That's another one of those quantum buzzwords I keep hearing about. What exactly is entanglement, and why is it so important in quantum computing?
Well, it's kind of strange. Even for quantum mechanics, it's pretty bizarre.
Yeah.
Basically, you link 2 or even more qubits together, and their fates are kind of tied together no matter how far apart they are.
Seriously.
Yeah, so it's like, imagine you have 2 coins, and they're connected somehow, so that when one lands on heads, you instantly know the other one landed on tails.
Even if they're like miles away from each other.
Yeah, even then.
That's crazy. It sounds like science fiction or something. How does this entanglement thing give quantum computers an advantage, though?
Well, because when we entangle qubits, we can create these really complex states that are impossible to create with regular bits. It's like you have this network of nodes all linked together, and if you change one node, the whole system is instantly affected.
Okay, I think I'm starting to get it. So by entangling qubits, we can do computations in a way that classical computers can't because of that interconnectedness.
Exactly. It's a whole new way of processing information.
One of the sources I was reading mentioned that quantum computers could break the encryption we use online, like for online banking and stuff. That's a little scary.
Yeah, that's a real concern. Quantum computers are a potential threat to some types of encryption, especially the ones based on factoring really big numbers.
Right, because there's that Shor's algorithm thing, right?
Yeah, Shor's algorithm is a quantum algorithm. It was discovered back in the 90s. And it can factor numbers way, way faster than any classical algorithm.
So our online stuff could be vulnerable to hacking.
Potentially, yes. But,
Yeah.
I mean, it's not an immediate crisis or anything. People are already working on new types of encryption, ones that are resistant to quantum computers.
So it's like an arms race, almost.
Kind of, yeah. Always trying to stay one step ahead.
I saw a paper about using quantum computers for drug discovery, like simulating how molecules interact. It's amazing to think we could do that with quantum computers.
Yeah, the potential applications are really incredible. Like, you could design drugs specifically for a person's genes, or create totally new materials with properties we haven't even thought of yet.
There was even something about quantum machine learning in one of the sources I was looking at. Could quantum computers lead to, a whole new level of AI?
It's definitely a hot area of research right now.
Yeah.
I mean, theoretically, quantum computers could change how we train AI, how we develop machine learning algorithms. We could tackle problems that are just impossible for classical computers right now.
So we could have AI that's not just faster, but, smarter, more capable of understanding complex things.
Potentially, yeah. It's pretty exciting to think about.
Okay, this all sounds incredible, but let's be real for a sec. We've been talking a lot about the potential, but what about the challenges? What's stopping us from having quantum computers on our desks today?
Right, that's a great point. Building a quantum computer that actually works is really, really hard.
How hard are we talking?
One of the biggest problems is that qubits are super fragile. It's really tough to keep them in their quantum states for long enough to actually do a computation.
Oh, right, because they can, collapse out of their superposition.
Yeah, exactly. The slightest disturbance can mess everything up. It's like, imagine you're trying to build a sand castle on a beach, but there's this crazy wind blowing all the time.
That's a good analogy.
Any little vibration or change in temperature can cause decoherence, and that basically means the qubit loses its quantum information.
So it's like that carefully built superposition just falls apart.
Exactly. It goes from this fuzzy quantum state back to just a boring old classical bit.
So how do we protect these fragile qubits from the environment?
Well, researchers are working on this, developing ways to do quantum error correction. It's basically a way of encoding the quantum information with some redundancy, so that if some of the qubits get messed up, you can still recover the original information.
Sounds complicated.
Oh, it is. It's one of the biggest hurdles we have to overcome if we want to build quantum computers that can actually solve real-world problems.
So it's like we're trying to build this super delicate machine, but we have to do it in the middle of a hurricane or something.
Yeah, kind of. It takes incredible precision. But if we can do it, the payoff could be huge.
So it sounds like we're still in the early stages, but there's a ton of potential.
Absolutely. And remember, we've barely scratched the surface of what quantum computers might be capable of.
It's almost overwhelming to think about. One of the sources even mentioned quantum teleportation.
Ah, yes, quantum teleportation.
That's where you can send quantum information from one place to another instantly, right?
Yeah, but you're not actually moving the qubit itself. You're just transmitting the information about its state.
Sounds like science fiction. Is that even real?
It is. It's one of the most mind-blowing things about quantum mechanics. And it all comes back to those basic concepts we were talking about earlier. Superposition, entanglement, and the ability to control these quantum states really precisely.
Wow. So all this stuff that seems so weird and abstract can actually lead to some really groundbreaking applications.
Exactly. It's like we're unlocking the secrets of the universe to build a totally new kind of computer.
It makes you wonder, what else is out there? What other secrets are hidden in the quantum realm?
Yeah. What if all this weirdness we're seeing is just the tip of the iceberg?
What if there's this like a whole other level of quantum weirdness that we haven't even discovered yet?
It's definitely possible. The more we learn about quantum mechanics, the more we realize how much we don't know. It's kind of humbling.
Yeah, it really makes you rethink everything you thought you knew about reality. If something can be in two places at the same time or instantly affect something else miles away, what else could be true? What else might be possible?
Exactly. And it's these mind-blowing aspects of quantum mechanics that make quantum computers so powerful. They operate on principles that just don't make sense in our everyday experience.
It's like we're tapping into this whole new set of rules, like a hidden language of the universe.
And by learning to speak that language, we're opening up all these possibilities that we could barely imagine before.
Okay, let's try to come back down to earth for a minute. One of the articles you sent me talked about quantum computing and consciousness. It even suggested that consciousness itself might be a quantum phenomenon. Now, that one really blew my mind.
Ah, yes, quantum mechanics and consciousness. It's a fascinating topic, but also a really controversial one. There are some interesting theories out there, but we're still in the very early stages of exploring this.
So we don't know for sure if our brains are using quantum algorithms yet.
Not yet. It's a very complex question. We're still putting the pieces together, but even the possibility raises some really profound questions.
It makes you wonder if we're only just starting to understand how deep and strange the universe really is.
Definitely. And who knows what incredible discoveries are waiting for us. Maybe someday we'll have quantum computers that can model consciousness, or even help us understand the nature of reality itself.
Okay, I'm getting a little carried away again, but it's hard not to get excited about all this.
It's an amazing field to be working in, that's for sure, full of challenges and opportunities.
Yeah.
And it's definitely going to shape the future in ways we can't even imagine yet.
Well, on that note, I think it's time to wrap up this deep dive. We've covered a lot of ground today. Everything from the basics of qubits and superposition to the incredible potential of quantum computing and the philosophical questions it raises. We've learned how quantum computers could revolutionize medicine, materials science, artificial intelligence, and maybe even challenge our understanding of reality.
It's been a fascinating journey through the quantum landscape. I hope we've sparked some curiosity in you and encouraged you to keep learning.
Absolutely. And I want to thank you again for being here and sharing your expertise. It's been a really enlightening conversation.
My pleasure.
And to our listener, as you continue your own exploration of quantum computing, remember to keep asking questions, keep challenging those assumptions, and most importantly, never lose that sense of wonder. The future is quantum, and it's full of possibilities that we can only dream of today.